So hello everyone to today's webinar, Keep Your Traffic Moving, Adaptive Signal Control with LISA and PTV Vissim. This is a joint webinar between Schlothauer Wauer and PTV. And this webinar we will give an introduction into the two software products, LISA and PTV Vissim, and how they interplay with each other. LISA is a traffic engineering software from Schlothauer Wauer. It is designed to plan, evaluate, and optimize interurban and urban road traffic networks. PTV Vissim is a microscopic traffic flow simulation tool. Two products which works great by themselves, but today we want to demonstrate how they interplay with each other and how you gain added value by using the both products together. My colleagues will present you the interface between LISA and PTV Vissim using a practical example of one common intersection. The presenters are, you'll see them. First one is Torben Titze from Schlothauer Wauer and Sebastian Reichert from PTV. Torben is from Berlin. He studied transportation and traffic at the Technical University Berlin and works since 2008 at Schlothauer Wauer and since 2014 product manager for network controls. Sebastian from PTV lives in Düsseldorf, also Germany, engineer from the Westfälische Hochschule, University of Applied Science. He is since 2015 at PTV Transport Planning and Engineering. His focus is planning for traffic signals. As you see the agenda, Torben starts showing how to build a node geometry in LISA and how to export to Vissim. Afterwards, Sebastian takes over the exported model from Torben and demonstrate the added value of the simulation in Vissim. There are two other colleagues answering questions during the webinar, and this is already a technical note. So please, you can post your questions using the questions window already during the presentation. This is Paul Schneider from Schlothauer Wauer and Lukas Coach from PTV. They are also both product managers. At the end, we'll also have a question and answer session. But as mentioned, you can post your questions already during the webinar. One final note, this webinar will be recorded and it's being shared afterwards so that you can watch it again. And now I'm very excited to hear starting from Torben about this topic. Torben.
Okay. Hi, Jochen. Thank you for your kind introduction. First of all, also a technical note and an excuse. It seems that my webcam was not handed over to the one that is not working correctly to the other one. So if you're wondering how I am capable of speaking so well and fluently without moving my lips, it's a technical failure, not talent at that side. Thank you. So yes, also thank you in the name of Schlothauer Wauer. We are very thankful that we get this opportunity to present our product LISA together with PTV to join forces and also join an audience or have a joint audience to give you an idea why it makes sense to not only focus on one of the two softwares, but to make them work together. Maybe a short introduction to LISA itself. What is LISA? If you're familiar with Vissim already, you know Vissim is a tool for microsimulation, and as Jochen has already mentioned, LISA is designed to evaluate and to simulate traffic actuated controls. Fixed timing plans, also unsignalized intersection, but the main focus is on the development and testing of traffic actuated controls. There, that is where LISA really shines. So what we want to show you today is that there's actually a benefit when you work with both softwares. We have the possibility to use the data that we are already introducing or entering in LISA, the geometric data, and export them directly to Vissim. So you don't have to do these steps of introducing geometric data twice. Yeah, short overview. First of all, here is this tab where you enter basic geometry and and facility data like signal groups, detectors, evaluation parameters. Then there's a large part where we calculate the intergreen times, where we design signal timing plans. We can automatically create them based on traffic volumes and traffic flows. And here over to the right, the logic part, where we have a development environment to help the engineer to develop a traffic actuated logic and to test it accordingly. So another thing that we will see is what other stuff can we do with this basic data. The keyword there, or the buzzword there, is map export car-to-X communication. That we will come to that also at some point. So I have changed here to the basic data entry panel. First, when we work with Lisa, we have to load a site plan, meaning we can open a little graphic. PTV was so kind to provide us with this intersection. It's an intersection, if I'm correct, based in Duisburg, West Germany. And as I enter this, upload this graphic, the first thing I am asked is if I want to enter scale. So I will do that. You will see that the cursor here is changing to this scale, to the scale icon. And if I'm correct, yeah, somebody was so kind to include a scale into this site plan. And we can just connect these two dots with each other. And now we are getting a suggestion based on the number of pixels per inch. Lisa will assume a scale. In this case, we have to adjust it a little bit. So the length of our measurement here should be 20 meters. And we can check that if we go into our plan, make a short measurement and say, okay, let's see how wide is this. Here's this lane. We have 2.90 meters, so this seems to be okay, more or less. So the steps that we have to do here, or why we do this, we are entering the geometric data into our software to tell it the geometric dimensions, so it can automatically calculate intergreen times, meaning the time between one stage, the transition between one stage and another. And therefore, the first step is to give it the access. And the idea behind this whole process here, or why we're doing this joint presentation, is that once this data is entered, that genuinely Lisa is just using for the intergreen time calculation, we can use this geometric data directly in Vissim, which comes in really handy and can save a lot of time. So let us see. We have here the this first leg on this side. The way it works is that you always go from the inside to the outside to also tell Lisa what is the approach, what is the exit. Now the tool has automatically changed, and I can just click on the middle of the lanes, and it will enter these lanes. I could make it a bit more neat to really hit the stop line here, but you will notice I will do this a little bit sloppy, to be honest, because we don't have that much time to be so exact today. I hope you will, you can forgive me that. So I will pull it here a little bit longer, let this to the middle. Did I miss a lane? No, it's okay. So here on this side, we shall not forget the bus lane that is here. So let's also go from the middle and click on the lanes. 1, 2, 3 lanes, and fourth one. Okay, I'll make it a bit more neat here. So We can already save. Oh, can people see my messages down there? Yeah, I know we were told to turn them off, but I'm actually not sure how to do it on this one. Okay. What I will do here now, I will extend these lanes further down the road. If you are an experienced Lisa user and you are familiar with older versions of the software, then you will remember that usually we're not able to do this because usually in Lisa we are only interested in the what is happening between the stop lines and not so much before the stop lines. Why did we extend this functionality? That is the topic that I have very briefly touched in the introduction. What we added in Lisa is a so-called map export, which means that when we talk about car-to-X communication, you might be aware of the fact that in the future, the goal to facilitate autonomous driving is to have a roadside unit with your traffic controller on the side of the road that will give the information to an approaching car of where is which lane is assigned to what signal group, and given information about the topology of the intersection. So that means that even from a standpoint of just the traffic control, or the traffic controller and the control logic, which is where what is Lisa's main domain of functionality, we also have to keep track of what is happening here in the approach to the intersection. So what we now can do is we can connect, make also connections, because that is also okay. Wait. Yeah, I have to introduce a new dot here in the middle. So, and having done that, I can even introduce a connection. This also is some kind of a byproduct of our new map export, and this also comes in handy when you export it to Vissim. If some of you have already worked with the already existing, the interface between Lisa and Vissim is already existing for quite a few years now, but this these connectors in the past, you would have to add them manually after creating the intersection, and now you can do that already at this stage of the development of the intersection. And I at least, yeah, that should end the messages. I just got the message that the audio quality might not be so good. Maybe someone can comment on that if you can still hear me okay. I'm afraid even if it was bad, there's nothing we can do about it, so I just apologize for that. I hope you can still hear me well and understand what I'm doing here. So what we have done so far is we have been taking care of the approaches. These axes that we entered will tell Lisa the geometry and the angles between the approaches. We can always check our work if we click on this intersection diagram up here. I haven't saved it. As soon as I saved it, yeah, it should be created automatically. So now I see all the lanes that I have done here. So now I will use this connection tool to make the connections between the different legs. Okay. Okay. I have to learn the tooltips also in English. I get it. The travel path is not L, L is leg. Sorry for the confusion. So shortcut P lets me make connections. As I said, I could be way more precise in how I do these connections. As you can see, you can change all these radiuses, so the travel paths are fitting better to the geometry of the site plan that I have in the background. But yeah, for the sake of the demonstration, as I said, I will do it a bit more sloppy if you like. So we have a left turner here we have to take care of. That's this. Left turner is done. I think, oh yeah, here's one leg that I haven't taken care of yet. Go over here. Choose a right turner and a left turner. They should not overlap then. Even if we're working fast, this should not happen. So this is the geometry of the for the cars. Then we can enter here the geometry of the pedestrians. So we do that by introducing these crossings. Yeah, if I wanted to be very precise, I can change the shape of the crossings. I will also enter here the bicycle lanes this way. First entering a crossing, then changing the mode to bicycle. Yeah, that is that. Let me zoom in so that you can see a bit better what I'm doing here. So I'm trying to catch the outer limits of this pedestrian crossing, so the software later knows where to calculate the conflict points. I'll also change this to bicycle. Not the pedestrian. Oops. You get the idea. We don't have to be exactly the millimeter right here. By the way, this should cross over all the way over here. I think this is a mistake that I did in the German version of this webinar a few weeks ago, and people wrote about it in the chat. Was it not? Yeah. Paul can confirm that. Yeah, please excuse if you should see stuff like that happening here. As I said, we're doing this a bit fast-paced, but still, it should result. So here, what we could do here, we can change also the transport mode of this connection here from vehicle to bus, and we should see that also reflected in our little diagram. Can I zoom out of this? Oh yes, I can. How neat. So yeah, this is also a great way to check if I have done everything correctly, because it has introduced for me these little arrows to give me an idea about the general geometry that I have introduced here. So yeah, it looks fine. I have a left turner. Oh yeah, except for the pedestrians and the bicycles down here in that leg. I will just keep it simple for now. You know that I could make it more precise, but we want to get to a point where we can start a little entry mean time calculation. So that should do it for now. So now this is the geometry done. So now is the next step would be to take care of the signalization. This can also be done graphically directly here, where we just or I just I can click on an approach, and then when I'm on the approach, I just add a signal group down here, and we will call this 1, 2, because that is the name of these of the signal heads that was given here. Sorry that the type here is in German. I forgot to load the English types when I changed the language. You probably wouldn't even have noticed if I hadn't said that. Okay, and here we just use 1, 2 as well. And we go through the cycle accordingly. 3, 4. We have 5B, if that's correct, or B5 over here for the bus. B5, and it automatically has changed here to a public transport type of signal for me. So takes care I don't make stupid mistakes here in the signalization. And seven, 8. Yeah, and then we basically do the same thing for the pedestrians. And we just call them P1 to P4. And this is we will say that this is a mixed bike pedestrian signal, and we just assign them to the bicycle lanes as well. So this is basically all the geometry data entered. We could have done it a little bit more in detail, like say put these radiuses a bit more where they actually are, but this is all here, this connection where they are waiting a little bit on the opposing traffic, but you see that you see the process, and you understand that it was basically a very straightforward and quick way to enter this data. And it's not only you might argue, yeah, but I've already done that. I'm doing that in Vissim. Why should I do it here and then export? Keep in mind, this software is mainly designed to help you calculate the actual data that goes to the controller, the data that shall help to ensure the safety and shall help to develop a working traffic control. So we have to be here a bit more precise about what is going where and stuff. So that said, if I take the data I have now, I will now change to another example, because what I would have to do now is I would have to enter the traffic flows, and then I can base my my calculations on these traffic flows, and I will spare you the pain of watching me entering numbers in a table. So we'll just change over to my prepared finished example, so I can show you what would actually happen from now on. So there are these evaluation parameters you see here. This is like the morning traffic. This was also provided to us kindly by PTV. We entered it here. It will also be exported then later into the network that you can import in Vissim. And yeah, intergreen time calculation. So one part is the safety part. So this intergreen time table was calculated automatically just based on the geometric data that we have entered before. You can change all kinds of parameters. You can change all kinds of speeds and distances manually if you want to or if you have to, but basically you have a tool where you're always on the safe side. All my distances and all my calculations are safe, and the safety measures are based on this tool. And the other side of the equation, the capacity, the level of service that you want to achieve, the signal timing plan that is capable of meeting the demand that you have entered in the volumes, that is handled here in the editor of the signal timing plans. And we have this little button here saying, okay, let's do an automated signal timing plan calculation, and just with a few clicks, I can get from just a flow and a few other parameters to this outcome. So this technical timing plan, based on the evaluation, based on the flows that were entered, is the outcome of about half an hour's work, which is pretty impressive, I think. So let's get back to our main topic, seeing Lisa and Vissim work together. This is the point where I have to mention people who know Lisa or know that Lisa by itself also has a simulation inside are asking, so you said that you should work with both these softwares. Now I see there's a simulation in Lisa. I don't really understand. Do I need both of them if I can simulate cars here as well and traffic and stuff like that? Yes, you do. First of all, being very proud of Lisa and knowing that's a very powerful tool, I think it doesn't stand a chance when you look at the simulation with what Vissim can do and how powerful it is in simulating and presenting traffic in larger networks. And we don't see ourselves as a competition in that field. So then you ask, but why do you have a simulation in the first place? This simulation here is a tool that is directly connected to our development environment that we have here. As I mentioned in the beginning, we can develop, test, and simulate traffic actuated controls. What is happening here in this editor is you are using Lisa to write a flow diagram of your logic. You are using a standardized library of controller functions that are mirrored in compatible controllers. So you're using a very accessible and understandable tool to develop real code, real traffic actuated control that is running on the controller in the real world, but you can simulate it here and you can debug it here. So whenever I have a simulation running here on that side, in the background, I have my control logic being in a debug mode, and I can set a stop point and go on with the simulation, and it will stop at this point of the simulation where I set my breakpoint, and I can go through the logic step by step by step and really follow what is happening inside. So just so much for where's the benefit of working with both tools. So for us, the workflow is develop a working control logic, debug it, make it so that you are from a functionality perspective really satisfied with the outcome. You say, okay, now I want to test it in a bigger context. Now I want to test it in a network. What this editor is not so good at is simulating more than one intersection. So as soon as you want to do that, go to Vissim. As soon as you want to present your results to a customer in a really shiny and state-of-the-art way, take Vissim. So that's what we're gonna do now. That said, from now on, it's only just one more click. You upload the logic to Vissim, and what it will do, it will create a representation of the intersection, an XML file and a jar file. The jar file contains a little, it contains the logic, or if you have a fixed timing program, this program in a little jar container, and that will later be running in the Vissim simulation. So it's basically just this one click, export it, and here we go. And then you have an INPX data file that you can open with Vissim. The one topic that I haven't touched with the last time I had touched a bit earlier, as I said before, we cannot only or do not only export Vissim networks, we also export our data in the MapX format. And there's a little thing that we have forgotten. It also helps us that the data, once opened in Vissim, has the right geometric reference. So as you can see here in my little example, I have here this little point, which is a so-called reference point. And here over there in the on the left side, I see it's a GIS coordinate, and this GIS coordinate can be taken from maybe from a plan, because you get this information from your customer, or as we did it in this case, we just went to Google Maps. We know that this is the intersection that we're talking about, and I just took this point where the lane is coming off and said, okay, this will be my reference point. And now what I can do, I can just copy the link that I have up here in my browser and paste it here into Lisa. So that's very handy. If you don't have a GIS coordinate at hand, but you want to use this functionality, you can just use Google Maps. It should not be your best way of practice, because Google Maps does a lot of projection to make all these photos fit with each other. So don't be too don't rely too much on it. But as a first idea, if you don't have any other information, it can be very helpful. So yeah, just to show once this would be then the outcome of the map export, we can show that in Google Earth, because the format is actually not so different if you just want to draw some lines somewhere in Google Earth. So we also have this as a byproduct, just to visualize for customers. Look, we can do this map export for the roadside units for the Car2X communication. So I think was I do about 40 minutes. Now we go over to Sebastian, but we also have some questions that we really have to answer. No questions so far. I see that Paul is shaking his head. I should go on. Okay. Now I was kind of hurrying up. That's actually it from my point. From my perspective, maybe more questions will occur later. I think it's also okay to have a little discussion in the end. So if Sebastian is ready, I would happily hand over to him to show what are the next steps once we have exported our network in Vissim. Thank you for your attention.
So then I would take happily over. So after the LISA export is done, we receive a bunch of files that contain our program signal control and the INPX file that contains the simulation model. We can now open the simulation model by double-clicking on the INPX file and should receive a window that looks similar to this one here. In the network editor, we can now see that the junction is already fully modeled. We have the links, the connectors, and the conflict areas are also modeled to set the right priority rules for the traffic flow. Furthermore, we also have the vehicle inputs and all vehicle routes implemented in our model and assigned here with the appropriate volumes. One thing worth mentioning is that for separate lanes, like for example here for the left turning traffic from west to north, we do have a single vehicle input instead of one input for the whole access link. This must be adjusted later for a realistic simulation, but for the first testing in our Vissim test mode, it's perfectly fine. So if we want to start our test mode to test and check our program signal control, we do have to get under test and select continuous test. Our test mode in Vissim is much similar to the test site in LISA. We do see here now that our signal control starts in the dark mode until we select our desired program. In this case, it's in program number 1. And we see now that the traffic signal changes to the ground state, where the roads with major priority receive a green signal, as well as the pedestrian crossings parallel to these roads. Without any traffic or further changes, this state would remain the same for the entire simulation in our test mode. If we, for example, select now this detector here and set a single activation, the traffic signal should switch to the state where these roads with minor priority receive a green signal, and we can set a single activation just by double-clicking on the detector. Like we see now, the control does exactly what it should do and should changes now back to our ground state where the roads with major priority receive a green signal. In the list of detectors, we can also set a repeated or continuous detection instead of just a single detection. Therefore, we can go by right-clicking here on detectors and then on show list and select some further attributes here. For example, we like to know the gap time of the detector, maybe the detection state, and the manual actuation state. If we now select the same detector, which in this case is the detector D3.1, we can select a repeated or continuous detection here. And in this case, there should be a detection whenever the road has a red signal, and the signal control should switch back and forth between the two stages. If we set our continuous detection now, we can see that the control does it perfectly. Like we see, does it perfectly. It can also be seen that the gap time here is 0, and if we would look on the occupancy rate, this should be around 100%. One of the great advantages of our simulation software Vissim is that we can not only test our signal control in our test mode. I would stop the test mode for this moment. But we can also test it with real traffic volumes. In this case, we can check how our signal control would perform considering the given volumes. Therefore, we click on our blue symbol right here, set our desired program, and we can now see and check how our signal control would perform with real traffic volumes. We also see that the roads with minor priority only receive a green signal whenever a detection, for example here, is set. To now evaluate this junction, we do have to do some minor adjustments to our model. The first thing we have to do is, like mentioned before, we have to delete, one moment, we have to delete this vehicle input for the separate lane. This is one here, and adjust the input for the whole axis link by 108 vehicles. As well, we have to do the same thing to our vehicle routes. We have the route for the left turning traffic with a volume of 0, which must now set to a volume of 108 vehicles. So, another thing is, if some roads of this junction do not have a speed restriction of 50 kilometers per hour, but maybe, for example, 30 kilometers per hour, we do have to add some desired speed decisions to our model. In this case, the southern approach does have a speed restriction of 30 kilometers per hour, so we add a desired speed decision right at the beginning of the link and set the speed to 30 kilometers per hour. As soon as we exit this link, we do have to set back our speed, so therefore we add also desired speed decision and set the speed back to 50 kilometers per hour. We do this also for the left turning traffic and for here too. Regarding the speed of the turning traffic, as for now, the traffic turns with a speed of 50 kilometers per hour. We do have to implement some of our reduced speed areas. For example, we set the right turning traffic here, and let's say they turn with a speed of maybe 15 kilometers per hour. For evaluation purposes, we now have to add evaluation elements, which can be found in this section here. We do have nodes, data collection points, vehicle travel times, and queue counters. And important elements for evaluating a junction are the queue counters that measure the queue in front of a signal and the vehicle travel times. Queue counters would be normally set at a stop line to measure the lane's queue development over time. For example, if we want to know the queue for the left turning traffic here, we can set and add our queue counter, and let's say for the left turning traffic from the western approach. To measure our delay times in order to evaluate the junction regarding the level of service concept, we must add vehicle travel times. For example, if we want to know how long does it take a single vehicle to go from here, from the western approach to the northern link, that means we want to know the left turning traffic from the western approach and set the vehicle time here. We would do this, or we would add these elements for all the relations we want to evaluate in the end. But due to our limited time, we have this model already prepared in advance, which I show now. We see here we have added data collection points to see if our modeled traffic volume consists with the traffic volumes that we maybe got from a traffic count. We have the queue counters at every stop line, as well as the vehicle travel times. It's now important to define our delay measurements out of these vehicle travel times. This can be done under evaluation, measurement definition, and delay measurements. Here we can set our delay measurements and set the according vehicle travel time. We already did this here in advance. And now we can simulate our junction in a realistic way and evaluate according to our national guidelines. After some simulation ones, we can open the result of defined delay measurements and evaluate the junction. We have to set a desired program first. Due to the time, we already did one simulation with 10 simulation ones and have the results list right here. And if we now check our delay measurements from our average one out of these 10 ones we did, we can create a chart of the results to visualize them. And we would now see here that our junction has a delay of maximum 43.7 seconds, which qualifies as a satisfactory level of service C according to our German guidelines. But not only can we simulate and evaluate this junction as a single object, but also in the context of a wider network. The great advantage here is that we can simulate and recognize possible trouble spots that maybe affect our junction. For example, in this case, we do have a roundabout nearby, which can be seen here, with a high volume of pedestrian traffic. If we simulate this roundabout like we did here, then we see that there's a queue here, and it's most likely to affect our junction that we modeled right here. If we do 10 simulation ones, for example, of the roundabout, then we would get delay times that can be seen here. And if we visualize them, we see we have delay times up to 330 seconds. And for this link here, we do have delay times around 120 seconds. So it's most likely that the traffic flow at our junction or signalized junction is affected by the queue from the roundabout. To simulate both our junctions in one model in context of the wider network, we can simply import our junction from before by reading it additionally under File, Read Additionally, and Network. Then we choose our desired network, which in this case is this one. Click Open. All settings should be left untouched, and by OK, we should now import our junction. We do see now that the junction is already imported at the exact same spot. And to now simulate both junction in context of the wider network, we do have to make some adjustments, like we have to shorten this link right here. Maybe this one a bit too, and shorten the link in the other direction too. To now connect our both junctions, we simply add a connector, which should, oops. And we do the same thing in the other direction. One important thing now is that we do delete this vehicle input as well as the vehicle input for the other direction, simply because if we do simulate this model now without deleting the input, we would have double the traffic in the model that we should have. So all measurements and all evaluation elements are already, with all definitions, are already implemented in this model now. And with that, we can simply simulate our both junction in context of the wider network. Like we can, well, takes a bit. So we see now that we do have connected our models and can simulate this wider network. And we also can add more and more junctions. For example, if we do have more exports from LISA, we can all read them additionally and create one great network. If we do simulate now, for example, 10 simulation runs, we would receive our delay time measurements right here. And if we now compare the average one and look at our results for the signalized junction from before and visualize them with a chart, we can now see that our delay is now up to about around 80 seconds, which qualifies as an insufficient level of service E according to our German guidelines. So now we know that our single control junction would be evaluated with a level of service E in relation to the network, whereas our single junction had only the level of service C. And this represents one of our great advantages of the simulation software Vissim, because the single junction would be evaluated way better than we would not have seen the trouble spots in the wider network. And with this, I would close my part and thank you very much.
Many thanks, Sebastian, and many thanks, Torben. Yeah, looks like very impressive tools. Good. And towards the end, we would like to come to a question session. I've seen there were already some questions posted during the session, and especially Paul was busy answering them. Lucas had an easy session. There were not so many questions for Vissim, and we would like to summarize. Paul, could you just summarize what were some interesting questions for everyone?
Yeah, of course. Thank you, Jochen. I had a lot of questions regarding LISA, and I want to group them in 4 big questions to Torben. So may Torben, can you show in the basic data how you enter detectors? If you have a traffic actuated control, where to place the detectors, what you should to be mentioned, and so on. Could you please show that in LISA?
Of course. Not that we hand over the control here.
So another question, I will just talk in the time Torben is opening this. So there was also a few questions how to upload from LISA to Vissim, and what you can upload, and if you have to modify the network in Vissim again. So Torben, how is the procedure? Do we have to modify the network after I did some minor changings in LISA, or can I upload the signal control or something like that?
Sorry, I was a bit confused. On an open microphone. Maybe I will first answer the question regarding the detectors now, because it seems that we're going to do it verbally. Yes, the same way I entered the signal groups in the editor, I can also graphically enter detectors in the basic data, and they will then first export it to the simulation network that we have in LISA, but they will also be part of the network that is exported to Vissim. So yes, there is a part that I went over at that point. And the other question was if I do changes in LISA or to the control, or
yeah,
yeah, the control. If you do you can export the control separately from the network. So every time you do an export, you're asked, do you want to export the whole network? Do you want to export the links? Do you want to export the geometry, or do you just want to export the control and the data that actually affects how the control behaves? So yeah, was that one of the question? Okay.
Yeah, that was
okay.
the answer. Thank you, Torben. Are there any questions to Vissim?
Question for Lucas, I think.
Lucas and Sebastian.
I think, I'm not sure, I'm not hearing Lucas. There was one question raised. What are the main difference using LISA and using VisWap? For those who are not familiar, I don't know, Sebastian, would you like to answer, or?
I think, did Lucas? Lucas is there.
Yeah, actually, I did answer that question in the question tab. LISA is a real traffic engineering workplace where you can create a control logic for real on-street controllers. You cannot do that with VisWap. VisWap is only for feasibility studies. You cannot export to the control for a real controller. Also, LISA has like the calculation of the intergreen times and so on. And well, in VisWap you have to do all that manually. It's not a traffic engineering workplace. You can only describe the traffic actuated logic in VisWap.
Mm-hmm. There were some new questions. Please, you can continue to post your questions, even if we can't answer all of them in this session. We will collect the questions and writing answers and distribute them to all of you. There came some new question. Is LISA just a design tool for calculation of intergreens staging plans, or could existing intergreens and plans be entered manually?
Yeah, I will answer that right away. Yeah, of course. If you have existing data, you can just you can enter them manually. It's not just a one-way road where you have to start from scratch, and it will only be an outcome of your calculation. Of course, you can just open an intergreen time matrix and enter the data that is existing. So you maybe want to do in a feasibility study or in a preliminary study some comparison to an existing control or to an existing infrastructure. So yes, that's possible. You can also evaluate that, by the way. So if you have an existing plan, you can enter it and then start an evaluation, and it will calculate the level of services based on German roadside manual, based on Austrian roadside manual. Several calculation methods are available, and we are extending them.
Okay, maybe because this is a very international audience today. Also, there was one question about if LISA can model adaptive systems such as Scoot or other international systems. Can you a little bit go into answering that question?
LISA has an interface with Omnia. Omnia being an example for a control that is not so much based on a single controller, but being a controller that works with a more capable traffic central that gives that is doing like a heavy load of the traffic actuated control. But that said, the main focus with LISA is to develop traffic actuated control that rely on a capable microcontroller of the types of Siemens C900, Swaco Actros, these kind of controllers that are compatible with the OCIT standard. So yeah, Scoots and Scats, as you may know, is a kind of a different approach, relying heavily on a very more central based control, where the main load of the actual calculation of the signal timing plan is done in the central, not so much in the controller. So yeah, I think LISA would be like a bit of too much of a tool to work with these controllers, because the functionality goes a bit beyond that what you would do with a controller that is working with these kind of systems.
Mm. Thank you very much. Already 11 o'clock. There are still questions. Someone raised, or people also raising hands. Please post your question to us, even now in the question window, or contact us directly, as you've seen on the screen, with our emails. Thank you for joining, everyone, and I hope that was a very interesting session. You learned something today from joining. Thank you at the presenters, Torben, Sebastian, also answering questions, Paul and Lucas. And we all wish you a very a good day. Thank you. Bye-bye.
Thank you very much.
Thank
Bye.
you.